Burn the box.
So I calculate, therefore I am, or maybe it's I am, therefore I calculate, if it's me, I guess. Yeah, I'm going to talk to you about math. So sit in for the long haul, as they say, 18 minutes of it. Well, let me start the story with Wolfram Alpha, which launched in May. So we call this a knowledge engine, or a computational knowledge engine. And as you can see here, it looks a bit like a search engine, but when you start typing stuff in, go ahead. I didn't think I would wrestle with a French keyboard on this, but we'll try and do it live. So you can type in something, and unlike a search engine, it actually computes stuff live. So it's going to take knowledge that's already been sucked in and made computational, curated. It's then going to understand what we're typing in and compute a result which is live for you now. So here we asked for the EU versus the US CO2 emissions, and you can see it's got understood the question, come in, used its knowledge, plotted a nice graph, etc. Let's try another example, a little bit more linguistic. What was the weather in London when Gordon Brown was born? And this is a little bit more linguistic, but we should still be able to understand the question, I hope, and come out with the answer. And it's going away and figuring out that live off the cloud that it's working from. And it comes out as overcast, cloudy, rainy, generally miserable. Okay, well, we can also do explicit math in Wolfram Alpha. And so we could do something that would come up in homework, like integrate sin x cos x squared, for example. And Wolfram Alpha should go away and go and compute that too. And now, to us, this is less surprising that we can do explicit math. You see it's come out with the integral. You can do much harder stuff as well and plotted various graphs. So yeah, thanks for typing those in for me. Let's go back to the main presentation here. So what I really wanted to talk about here, there are many things to talk about with Wolfram Alpha. There's how we suck in knowledge, how it changes in the new era of knowledge, the ways that governments and companies should use their knowledge assets to the fore, how we work with those things into the future. But there was one question that came up that I really wanted to talk about here. And if I can get things to work, yes, great. The question that came up so often is it cheating to use Wolfram Alpha for math homework? Now, to us, this is sort of a slightly surprising question, because we've been building math software for 23 years. One could always have asked this question, and people have, but particularly it's come to the fore because Wolfram Alpha is so much there on the web, and as you can see, you can type explicit math straight in. And we decided 23 years ago, people told us don't build a company on math. Nobody does math. Well, they were wrong, and we just decided we'd build a math company anyway. The key to this is mathematicians are not the main users of math. All of you are. Although you maybe don't think of yourselves as mathematicians, the use of math is greater than any point in human history, and is accelerating. We use math in all different ways, whether it's in technical jobs or whether it's in everyday living. Math is actually really very popular these days, and it's kind of important to understand that in terms of what we're trying to do. We're trying to automate and democratize mathematical computation. And what I showed you at the beginning in Wolfram Alpha is all math and computation. The first examples didn't look quite so much like that. The last one did, but they're all really math. So computation has really come of age at this point. And in the real world, people do math and computation with computers all the time. The math has changed a lot from its 2,000 or 3,000-year-old history. Now, there's one big area where this liberation didn't occur: math education. For some reason, we just insist that our entire populations go through learning how to hand calculate everything. Solving equations, finding inverses of matrices. Why does this make sense? We could be spending time getting them to conceptualize things instead, just like people do in the real world these days. So let's talk about why we teach math. What's the point of math? Well, it's a good question if you asked it to many students. Well, I think there are 3 reasons, if one's brutal about it: technical jobs, what I call everyday living, making sure that people can live and understand government statistics, these kinds of things, and what I would call mind training or logical thinking. Let's go one step further. What is math? What do we mean when we say we're doing math or learning math? I think there are 4 pieces to this. Posing the right questions, that's the really key one, the one that gets screwed up almost all the time in real life. Real world to math formulation. It's kind of an encoding exercise. You take the real world and you make it mathematical because math is so powerful. It's great to have things encoded mathematically. That's what we've done with Wolfram Alpha. Then computing the result you want in a mathematical form, and then going the other way, taking the math and turning it back to the real world, understanding what it means, verifying it. So guess what we're doing in education? We're mostly getting step 3 done by students, and step 1, 2, and 4 done by teachers. This doesn't make any sense. Why don't we get step 3 done by the computers, just like in real life, and get the students to do steps 1, 2, and 4, what they actually need in real life? So the big point here is math doesn't equal calculating. Math is a much greater subject than calculating. So let's stop pretending by spending 80% of the time for all the students doing calculating. I used to like this British comedy series, Yes Minister, about the goings-on between politicians and their civil servants. And there was a nice concept they had there of politicians' logic. And politicians' logic went something like this. My cat has 4 legs, my dog has 4 legs, therefore my dog is a cat. I'm sure it's familiar in this building. Well, now we've got politicians' math. We need math for the knowledge economy. Math equals calculating. Therefore, let's make sure everybody learns hand calculating. And we're being pretty successful at it. Today, by my estimation, 15 million hours were spent by students learning hand calculating in the EU, just during this conference. That's 23 whole EU lifetimes. I think of calculating as the production line of math. And, if you want to build a car, for example, it's normally it's good for most people to be off the production line. You want to get the production line automated as much as possible. You don't want to be on the production line if you can possibly help it. Well, computers allow us to get off that production line of math. They allow us to do something very different. And that's kind of what we want to try and achieve. Well, okay, so there are skeptics. People say, like here, I'm skeptical about these changes. And I wanted to touch at least 2 of the main things that come up in the skepticism business. So one of them is, you got to get the basics first, Now, presumably what they mean by basics is you got to learn the hand calculating first before you use the computer. I just don't buy it. What do you mean by basics? It's basics of using a computer, learning to build it with a soldering iron and putting the circuit boards together. Well, it was one day when you needed to do that, but it isn't anymore. We don't suggest everybody goes through soldering classes, for an hour a day all through their lives so they can use a computer, or that they learn to build a car so they can drive it, or that they learn to sharpen a quill, for that matter, so they can write. Nor should we with math. So it's also interesting that sometimes people mix up the historical order of invention with basics. And a nice example I like for this is paper and computers. Just because paper was invented before computers, it doesn't mean we should do all our math on it before we teach people how to do it on computers. My 4-year-old daughter actually had a rather nice anecdote she gave me on this. She enjoys making what she calls paper laptops. Actually, I even brought a custom-made one for the conference. So you can see what you do with a paper laptop is you draw the screen on the top and keys on the bottom. And I guess this is a widescreen model. So I said to her, when I was your age, I didn't make paper laptops. Why do you think that was? And she thought carefully for a second or 2 and said, no paper? Okay, another argument is the mindless button-pushing argument. that if we get people to use computers, they'll just mindlessly use them and they won't understand anything of the concepts. You mean that they really understand the concepts now and they don't find manual calculations that they do in math mindless? Hey, which planet are you living on? Ask most students whether they find math mindless or not, and I think you'll get a pretty definitive answer to that. So we're starting from a pretty low base in manual computations on this one. I think we can be far more conceptual with computers. And, if you want to see how this has worked, look in the real world. Do you really believe that science and engineering and the other things that depend on math in the real world, whether explicitly or implicitly, have become more or less conceptual in the last 20 or 30 years? It's much more conceptual. There's no question about it. They haven't been dumbed down by computers. No way. It's been the opposite. The computers have liberated people to do the concepts and think through what's going on. So I think we can make math both more practical and more conceptual. This is kind of a silver bullet by having computer-based math. This is a very rare possibility. In most subjects, one's got a choice kind of between the vocational and the intellectual at some level. But in math, I think we now are able to improve both simultaneously. And, it's one of the examples that is given us by a keen, Mathematica user who's very, Jerry Yule, who's a very keen advocate of changing math education. He says, if you give the average child, if you talk to them about a cat, you want them to know what a cat is. Do you tell them it's a feline quadruped with an aversion to water, or do you give them a kitten to play with? We've got the kitten to play with now. We've got a system where you can actually play with it, interact with what you're doing. You don't have to have the theoretical description before you start using it. See, I don't know why we don't teach calculus early. Well, the reason is typically because computationally it's hard. So you've got to wait until you get to the computational stage where people can manipulate everything by hand to teach it. But actually, I don't think we really should do that anymore. I think we should focus on the conceptual order. And, you can teach stuff much earlier if you do that. I mean, this is a very simple example, sort of primary school. And I'm going to change the number of sides on this polygon, as you can see interactively here. By the way, I'm running Mathematica here through this slideshow, and so this is all interactive, of course. And you can see it's pretty obvious what happens in the limit. Any 3-year-old could tell you. It turns into, or 3 or 4-year-old could tell you, it turns into a circle. That's the limit of what happens when, it's a very simple example. Obviously, for that audience, you also need to be able to do things like, actually, I guess it doesn't work for a circle, changing the angle, but the color certainly does. There we go. It's a very important feature of that demo. Another thing that's got to be reformed is the way we assess people. And, if you look at how exams, people say this, math is a very binary kind of subject. The answer is right or wrong. Well, that's true of calculating. It's not really true of math. The kind of math I have to do every day, here are the statistics out of our website. What do you think we should change about the website? That's not a binary question. That's a complicated assessment question of which question to ask and all the other steps I went through. Well, we should have exams like that. And once we have computers in exams, we can do that. And here's an example. This is a real-life life insurance model made by an economic lawyer, Professor Seth Chandler, and he's posted on our demonstration site, which has lots of these kind of models. This is a real piece of research. And you might ask the question, what's the best life insurance policy to have? And you can actually change this, and you can probably see aspects of what's below moving and changing. So you start, this isn't the only type of question you should have, but you can imagine having optimization questions where you're really trying to pull through what's actually happening there. It went red. That was I thought there was a nice sound that came with the redness as well. So. Okay, so we've got this real chasm between kind of the real world math and, gosh, it must be listening to math that does it. We have this chasm between what we call, real-world math and math education, which we've kind of got to climb over. And, my point is, if you just walk very slowly, this is what happens as you go into the chasm. You just walk straight into a chasm unless you want to actually make a real flying jump at it. So let's demonstrate what happens if we improve our initial velocity and try and jump over the math versus math chasm. Like so. You get to the other side. So what I mean by that is we've actually got to really strip out the hand calculator. We can't just decide that we're going to add everything in, make it all computer-based as well, and let everybody do this. We've got to strip it out to the basics that I call the basics and go back and re-engineer all our curricula to make sure we can really teach people. And then governments won't be coming around all the time and saying, you know, I can't understand why math education is doing so badly compared to what people need. It seems to continue to decline based on what they really need. I guess there was an extra feature here of saying, go for it. And the little guy pops up there. But, you know, it's scary making a big change like this. A lot has to change. But the change is absolutely necessary. I'm convinced that the first country that really makes this change will have a huge benefit. And it's kind of interesting to think about, we had a lot of talks this morning about the developing world. You know, I think that this is one way, adjusting how math education is done in the developing world is both something you can do probably quicker than in the developed world. There's less infrastructure to change. But it also has a huge impact. Think of all the high-powered jobs that depend on understanding math at a conceptual level. It's something we can do relatively cheaply and easily. So it's a real thing for the developing world to be able to leapfrog the developed world. But it's a change we need to do everywhere. And it's very nice, by the way, to see that the Danes have recently started introducing a pilot study of computers in exams. It's not on math yet, but it's a great start anyway on going forward in that direction. So looping back to the cheating question, I would claim it's cheating not doing computer-based math. Because we're cheating students out of real conceptual understanding and an ability to drive much further forward in the math they can do, to cover much more conceptual ground. And in turn, that's cheating our economies. You know, people talk about the knowledge economy. I think we're moving forward to what I would call the computational knowledge economy, where we've kind of democratized high-level computation across a wide range of people in the way that knowledge has been democratized across a wide range of people who are driving our economy. But we need to educate people for that as well as give them the tools and let them use the tools. And finally, it's cheating the fun out of a great subject. And, you know, I think we can make math much more fun, much more engaging, if only we base it on doing computer stuff. Whoops, now... let me go back. This is a guy called sort of Algebra Man, and I'm going to try an experiment here, which is to plug a USB joystick in, actually in real time, and the chance of success here is fairly close to 0, but nevertheless, hopefully it's just easier rather than pulling sliders and stuff. Yeah, well, that's the problem with that. Let's try once again to see if it'll. Let's try to select it differently. And see whether we can actually, oh yeah, amazing. We can actually change this guy as well. As you can see, he can go into rather weird configurations. I was actually trying to get him to smile. Yes, there we go. Just about. Well, it is a math talk. What can you expect? And by the way, we called him Ted of X. Thank you.